Hi, and thank you for your interest in our research on non-parametric approaches in setting safety stock levels. I am grateful to be joined in this research by my colleagues Brad Price and Doug Thomas. In global supply chains, we often encounter long and variable lead times for a variety of operational conditions. In our research with industry partners, we've found that this leads to lead time demand distributions that are often multimodal, left or right skew, and in general non-standard, like this example of a raw material skew that we feature in our research from our industry partner MANAGERIAL. As a result, textbook assumptions like normal and gamma do not work very well. The other problem is lead time demand is not tracked in practice, which means that the estimates for the lead time demand parameters have to be developed from the lead time empirical data and historical demand data, which often result in accumulation of errors that result in problematic estimates. So managers often do not rely upon these approaches that are built into their ERP systems and develop their own workarounds that can be quite elaborate but yet imprecise. In our research, we set out to determine if our proposed bootstrap approach can actually provide better estimates than the textbook approaches. We do this in the context of a continuous review inventory policy for a fixed order quantity where the reorder point is set for a target service level. Our non-parametric bootstrap approach bootstraps mixtures of lead time demand data from empirical lead time and historical demand. We provide a central limit theorem that also helps us to provide a confidence interval for these bootstrap estimates. And we use extensive numerical experiments to prove our theory as well as to determine the tuning parameters for our bootstrap approach. And we will also talk about a pilot implementation with our industry partner MANAGERIAL. Firstly, the tuning parameters that we determine from our numerical experiments tell us that we need to set the bootstrap resamples at least 500 to get good bootstrap estimates. In addition, we also find that our bootstrap sample size of each resample has to be set equal to the lead time sample size, the empirical lead time sample size. And if we provide a bootstrap resample size larger or smaller, we will get biased results. We also find that for a lead time sample size and therefore a bootstrap sample size of 24 data points or more, we would get the best bootstrap results. We find that the bootstrap is robust to various lead time demand distributional forms, which helps because now managers don't have to find out what is the distributional form of their underlying lead time demand data. One thing we have to do is exercise caution if you are going to set very high service levels, that is, when you have service levels at or greater than 98%. When we did our analysis with the MANAGERIAL's test skews, we found that the bootstrap even did better than the gamma, which we found to do much better at smaller sample sizes. Like we show in this graph over here, where we can see, especially for skew 3, the bootstrap provided a much better estimate. As a result, MANAGERIAL went ahead and implemented our approach, for which we provided R packages and a Shiny application, which are available from the author team, and implemented this for 9 of their high-value skews. Over a 15-month period, we found that MANAGERIAL saved close to $1.2 million in inventory costs and an additional considerable savings in facility costs. But most importantly, the managers really appreciated the confidence interval for the bootstrap estimates, which allowed them a range of safety stocks to determine and see whether the safety stock would result in excess inventory investment or in a stock out cost. We want to thank our friends at our anonymized industry partner MANAGERIAL. Without their help, this research would not be possible. Thank you.